Jimbo's going to take you down a route and present some things to you now and introduce you to the world we need to be looking at to put this technology to good use. So I think now's a good time, Jimbo, to start yours.
Yeah, as good a time as any, I guess.
Yeah, okay. I'll screen share it and you just prompt me when you want things changing, mate. I can find the folder. Stand by. Here we go. I can pause this.
So this is an electronic layout of what they call a cat whisker radio. It was a simple device that could pick up through an antenna ground system AM signals out of the air. It's a little piece of wire, a coil, a ground to a kitchen sink, and a couple of capacitors. And the D here is actually a small crystal of gallium, a lead oxide, and allowed you to well, clip the AM signal and hear it through the microphones, if you will. At the end, the E is a set of speakers, of dynamic speakers. So I guess that's good for that one. Hello?
Yeah, I was following it, Jim. I don't know if it jumped too far ahead there.
Yeah, there you have what they call, well, the armature for cat whisker radio. If you didn't get a signal, you'd lift up the little piece of wire on the little rod and reset it down and do it till you got a radio station. And that was basically poor people's radio at the time. But it worked well. There were millions and millions at one point. You only see them in museums and stuff. So I guess we can move to the next one. Okay, in electronics you have like components, and the most basic are the resistor, which we see the symbol for a little ceramic resistor or a carbon resistor here. And there's a numbering system. The first two numbers represent, the values, and third and fourth are multipliers. Then you have like tolerance, which is whether they're 80% efficient or whatever percent they're. It's just a way to know what you're dealing with and the quality of your components. So we can go to the next one. You should see a bunch of examples of resistors. And in general, the bigger the resistor, the more power they can consume, more they can take. They get hot too, so never touch a hot resistor. It'll burn you. But there they are, and they're all color-coded, ceramics included. The one at the very end, the 5 watt.
Can I ask a question?
Sure.
Okay, and you might know the answer. So in an electrical circuit, okay, so if it's a closed-in circuit, because I really am not as well versed with actual electricity as I should be, but in a closed circuit, when the energy hits the end of the circuit, would it start back over or would it go back the other way?
Technically, it grounds out.
Okay, so it just stops.
Yeah, it like goes to the. It's supposed to, if it's a battery system, like a 1.5 volt battery, it flows through the circuit and then winds up back at the positive end, draining.
Okay, cool. Thanks for answering.
Because with our system, we see the electrons as moving from the negative to the positive. Oddly, the British system has the electron move through a series of positive holes, and they call it positive to negative system. So you couldn't wire a car the same way here as you would in England or European cars. You'd blow up stuff. Burn out components.
Typical, huh?
So then, speaking of our Earth system, when you're talking about, something following its path, and so no matter what, it's going to have to continue on, say, under the surface to get back to the other side. It's going to have to be a continuous loop.
Yeah.
Okay.
Basically like a magnet. One young lady in New Zealand, I think it was, or Australia, was able to photograph the magnetic lines leaving the Earth, going up towards, well, I guess the dome or whatever you want to call it, and then back down to, Earth at another spot. So she was able to capture those waves,
I would say they could probably be localized waves within the torus field of the local rainbows, Jim, that when you think about
smaller
that.
ones too, yeah.
Yeah, so, what people are calling a dome, we're seeing, well, half of a torus field basically sticking way up above ground, aren't we? You look at a rainbow and relate it to a torus field, it's on top of a torus field, and that's probably what they're actually measuring. Very interesting. Do you want to move on to the next?
Yeah. So this is a resistor and a capacitor with a low voltage battery. Now, this is a very simple looking circuit, but it's called a timing circuit and also a filter circuit. So depending on the value of your R and your C, you can have 60 hertz flow through or, 10 kilohertz flow through. An RC circuit is used to filter different wavelengths and allow some to pass and some not to. So they're low, medium, and high bypass, bandpass filters, they're called. So it's just basically a resistor with a little capacitor, and it can help to control traffic in a circuit, and that's its purpose. To control when things happen, by timing things. So we can move on to the next. Most electronics in your home and TV, don't matter what, you start plugged in from the wall and then you go to the back of your TV, whatever it is, and your AC current is going to go through a transformer and then through what's called a full wave bridge rectifier. It changes AC current, it rectifies it, it corrects it, and makes it a DC, a continuous direct current. So for most electricity to be usable, most often it's direct current we're using, what we call DC. And this is a circuit that simply helps to convert from AC to DC. So we can move on to the next.
I love that picture. It reminds me of something I'm working on right now. That one right there. I'm working on showing the Earth energy system and how it, goes from ground up to the clouds and back down and around. Anyway, it just reminded me of it the way it's laid out.
Yeah, one thing you can note is that the direction of the arrows is the direction of the current flow. This is again a what we call this circuit is to mix two signals together, so it's to make harmonics, or harmonic generator, if you will. But it's also okay. You got the headphones at the back, but this blends two signals together, and then allows you to use them. But when you have coils like that, it is just for that. Make a mix, a blended or a heterodynes signal. So everything's about signals, just detectable information, whether it's bits and bytes for computers or audio that comes in FM or AM. It's all about treating signals, capturing them through an antenna ground system and processing them to, well, hear your music or, play tanks or whatever. I guess we can go to the next one. Yeah, these are basically like elaborate diodes, but they have a little more to them. These are PNP transistors and NPN transistors. What they do is they allow you to apply a small signal to the base, and it'll change the current exactly relative to the amount of change on the base, but amplify the signal as it goes through. So these are used to amplify stuff.
Opus has a question for you. Is that how I would mix two DC square waves from different devices together?
Yeah, you could, and you'd mix them through. You could still send them through a bridge rectifier. It would still work. Now, here we have what we call a basic layout for a super het radio. Basically, it's a radio that can transmit and receive, but also play music or do whatever. You have a variable frequency oscillator, an RF filter. You have a beat frequency oscillator, the BFO. Basically, IFs are intermittent frequencies. You need to capture a signal and do a lot of amplification and treatment to it, filtering of it before you can actually, get your detectable information from it. So a lot of these things are built in stages and stuff, so that if something burns out, it's usually one stage or one set of components, and it sort of makes it easier to fix. So we're good on this one. And all of this stuff, even though it's symbols in this, it's metal junk and coils of wire. Like here, this would be coils of wire wrapped around, little ferrite cores or something. And where it says C1, it's a variable capacitor. It's like two aluminum plates that are separated from each other, but you can increase or decrease the amount of surface that they each face and change the capacity or capacitance of your circuit and get different frequencies to come through. In this one, by varying the C2, you get different radio stations, basically, by changing C2. That would be a knob that you turn, connected directly to the aluminum plates. So I guess we can go from there. These are samples of capacitors. The ones with the moving plates, well, the two that look like they got waffles on them, those are your variable capacitors. They allow you to turn and tune to different stations, the radio, or sometimes it might just be different frequencies on a treble, on a amplifier or something, some type of, preamp, if you will. But basically, the larger they are, in general, the more current they can, more voltage they can, more electrons they can hold, and the more dangerous they are if they're not drained properly. If you touch both ends of a hot capacitor, you will get a shock. Normally non-fatal. We're good on that one, I guess. So these are ferrite cores and transformers, basically. There are different kinds in this for different uses. Some are for radio, and some are just for changing your voltage, getting higher voltage and current to a circuit. But they're all just mechanical and, usually often handmade. In the day, they were all handmade, now you can go to a shop and buy what you need, wrapped and already valued, if you will. These are some symbols for the different types of inductors or coils. Often it's coils of wire around a metal core of some kind. And the metal core amplifies the power or the magnetic ability of a coil, or a piece of iron for that matter. If you wrap a nail with insulated wire, pass electricity through the wire, it'll magnetize and pick up other nails or do whatever. It becomes an electromagnet. Very powerful devices. These are some of the coils or yoke cores that are used for televisions on the back of the old cathode ray tubes to deflect the electron from the cathode ray tube to draw the image on your screen. They were able to deflect it from the top right to the bottom left and cover 400 or 500 lines of image 30 times a second. It was good technology, but again, very, very primitive, if you will, by today's standards and stuff. Here's some of the old electronic junk. Some is still used today, depending on the equipment and the needs. But these are a bunch of ferrite cores. They're just made to be wrapped with insulated wires and produce a magnetic field for whatever purpose. So we're good on that one. The E-shaped ones are often used in televisions and larger transformers. This is a smaller, radio transformer or coil. These would have been used in a lot of the old televisions and a bunch of the old AM, FM radios. You see a bunch of these guys in them. It'll have a specific number of turns or windings. This one has several windings, but again, gives you different frequencies and different amounts of, a magnetic field that collapses over time. So they probably needed different amount of backup energy, if you will, because they store, and if the power drops in a circuit, the coils can help to keep it fed until it gets new juice. So in part, that's what ferrite cores are for. Sustain EMF, the electromotive force. That's a ferrite core on a USB power adapter, I guess. Helps to cut some stray frequencies, but it also builds an EMF or an electromotive force, so it can continue to give a little bit of electricity, even though the power behind it might be reduced or not being strong enough. So they're just sort of a precaution. Make sure you get enough power sustained. And there's one of the yokes on the back of an old TV. Those would produce between 24 and 36 kilovolts of positive or negative charge to deflect the, and there's the hole that you can see up higher. That was to put a positive on the screen and on the phosphorus on the front of the tube where you see the image. A lot of voltage between those two surfaces, the vacuum. More ferrite cores. These guys are usually for radio, TV. They aren't used very much anymore. And they are very fragile. It don't take much to break them, chip them. And there's another basic cat Whisker radio with the diode. It shows a basic antenna ground system. The A1 is the antenna, and the GND is your grounding area. And they have a variable coil inductor there, L1. Again, you could put a crystal of gallium at C2 in that circuit, and basically you got your tuner for AM/FM radio. And this is just how to draw like intersected, connected, or non-connected lines in a circuit board, or hand-drawn circuits, so you know what's connected, what's not actually.
Fantastic, Jim. Good information, mate. You guys in chat, I wanted Jimbo to go through this with you, because we do need to start understanding electronics more and working with it more. The reason being, like what we discovered. Hold on a sec. I'll just stop sharing that. Find where there it is. Yeah, I'll just show you this, and I'm going to hand it over to you. There's not much more to show now on this part of it.
I just want to say that was absolutely awesome, because if you remember all those lines I was doing on Google, Jimbo, a lot of those pieces look like what's, in the Earth surface.
Circuitry, yeah.
Yeah, like that's pretty cool.
Isn't it? It's like the old remember the sigils? That's the one you're talking about, isn't it? The little circuit diagrams. They've always been here, haven't they? They've just they depicted things differently, it seems, with these circuit diagrams. Right, where's this video I want to share? This one here. Just share it from here.
Well, like an iron plate with a little rust might as well be an inductor, Yeah. React the same as a coil, basically. No matter how big or small. In fact, ferrite cores are often not just a wire, little piece of iron oxide or real cheap iron that's used in electronics. Becomes an important component, It might seem like dirt or rust or whatever, but has a purpose.
I'm just going to drop 2 links in chat, people, for 2 channels that's going to feature. I'm going to feature a little bit of their work in a video I'm going to show you now. One's bigclive.com and the other is Creative Techos. Now, if you remember from the alternating current decoder of the Milky Way, which is what's on screen here, and what I discovered with solar panel afterwards, where's that? This here. Now, well, let's go back a bit. Right, yeah. So this is an air pump that was pumping air into a water barrel during the day, but at night I noticed there was a polarity switch and it reversed the flow. So this is how we knew there was a definite switch between day and night taking place in this construct. And what happened was it instead of pumping air into water, it was now sucking the water up the pump, up the cable, up the tube, up towards the pump. Now that motor on this, there's a little 1.5 volt. Well, it'll actually run on 1.5 volts. The motor inside that yellow case, and the voltage it detected at night was 1.9 volts. So it was enough to run that motor at night, and that's what was causing this reverse flow. Now on solar panels, they put what's called a switching diode on to stop it doing it. But what we're discovering is there's power there at night time. We just need to be studying it a bit more, and what can we do with it. So I found what I was doing. I was looking for a circuit that I could utilize this switch at night, and I've come across bigclive.com's channel, which is on screen there. So I reckon you subscribe him, and I found this video he made a few years ago, which he figured out a circuit where he basically put to use what he called a leak. He thought he's saying it, most people is calling it a leak, but it's not a leak. It is a definite switch in polarity. And this is Mama Angel testing a solar panel and lights that I made this circuit with. So, you know, go to Clive's channel. If you want to make this, it's a project I recommend you, your kids, everyone gets involved with, because it's a good, fun project, and you know, it's so cheap to make, and you can see little uses there. Now, you know, scale this panel up and you've got a lot more power going on. Obviously, you need a bigger battery. This is just a small solar panel off eBay, a protected 3.7 volt battery, and some components. So simple to make, and you know, I just lumped that together to show that how it worked. And this is a circuit diagram I made of it for myself to show you what's that circuit. So you know, this is a little project you, your children, everyone should have a go at it. You know, this isn't hard to do. It's very easy. You don't need to understand any of these components. You can learn that as you go. This one here learnt me a few things. I don't understand. I understand some components, but not a lot. And there's the other channel that I noticed had a battery level indicator circuit. So I thought, well, okay, can I you know, find if it's charging or not? So putting this in line, I found it was starting to eat the battery more. So I put a momentary tactile switch on there, so you just press when you want to check the indicator. You know, this is an optional extra that I thought would be useful for that circuit. And that would be that circuit now added into the other circuit with the schematic. So that's what I made myself, and it works. During the day, it receives light and charges. It detects nighttime coming on, and it switches on automatic. And as long as it's had enough light through the day, it will run till sunrise the next day, just about. You know, I've seen it run all. I've got up the next morning, and it's still been on. Just before, you know, as it starts getting light, you'll see the light starting to dim, then it switches off and goes back into charging mode. Very easy project to do. You can get a lot of these components scrap and for cheap off eBay. And, you know, what I want to do is send this panel to someone with this circuitry on, and, you know, have them analyze it. But from what I can see, you know, it seems to be, the circuit seems to be utilizing what Clive calls a leak, but what we're seeing is a polarity switch. And this circuit seems to work fine with it, and charge during the day and discharge during the night. Very clever stuff. But, you know, that's the important thing we want to put out there. There is a definite polarity switch between day and night, and it can be detected, like I showed you with that air pump. So that was what I wanted to show you.
Yeah, sensors and transducers. See, we're basically a sensory system there. We have built-in transducers and stuff. We take in a lot of information at once: the audio, visual, smell, taste, other feelings of touch, you know. And all those signals go into us and, well, have to be separated and processed and reacted to usually. So that's pretty good.
That's not much difference, you know. Hopefully people are going to start seeing connections here with what Jimbo's explaining. Let's go a bit deeper, Jimbo, shall we?
Yeah, well, our senses are basically electronic devices. Like, you know, when we smell something, the chemicals don't go to our brain. An electrical signal, a frequency is sent, you know, through the nervous system.
Yeah.
But it means smell is electrical, you know, magnetic, if you will.
Yeah, and we're just taught to give it words and explanations.
Yeah.
Yeah, makes sense, doesn't it? It has to be explained somewhere or other. Let's see what's next. Ooh.
Yeah, the crystal skulls. Now, there are a lot around, but not all of them are real. And the real crystal skulls, if you hold a laser to the base of the spine, it'll, well, expose the electrical paths that were there before it became crystallized. Like neuroelectrical paths to the eyes, to the ears, to the nose.
Yeah.
Pretty amazing. A real skull. That's a fascinating thing.
That's kind of like the petrified ones that you noticed, remember, with the bones sticking through and things.
Yeah. Yeah. A lot of them are just made of quartz and hand-polished quartz and stuff. But the real ones, genuine head there. One lady in England has one. Creepy. She's holding it up and showing it off there. And they did lasers on that one and a few others there. Again, these are microscopic paths that, well, electric signals flow through and stuff, and they're exposed with these lights. And, the fact that they're preserved within a quartz structure, and it's just unbelievable. We can't control crystallization to a fraction of that. Whatever did this had power, had knowledge, had something, that we don't today. Yeah, these are supposed to be where certain, like voice control, speech control, whatever, are controlled in areas of the brain. Frankly, I look at it and I kind of say, well, okay, because I don't think we really know where, thought comes from or goes, or how it's stored, and when there's brain damage, how information is routed to other parts of the brain. We don't really know enough about all of that, so...
Interesting is left-hand rule and right-hand rule going on, just like with the halos, isn't it?
Yeah, absolutely. And I don't know why, but yeah, we're divided into predominantly left and right hemisphere brain.
Like an equal and opposite, like nature's got.
Yeah, I'm left-handed, so I'm in 10% of the population for whatever. It's supposed to be different artistically and etc., But I don't know.
Yeah, I suppose you could probably test that somewhere or other.
And a lot of people don't know, but the brain, if someone calls you a fathead, thank them, because basically the brain is about 70-80% fat. So it is a compliment to be called a fathead.
Yeah.
Yeah.
If it's put to good use.
Yeah.
Yeah. Or it's not much use otherwise, is it?
Well,
yeah.
Bang here.
Let's move on.
Oh, here's a little circuit that's almost like, it shows an antenna ground circuit where radio waves right out of the air can be picked up, amplified, and make a speaker play a radio station for you. But this is a simple circuit that gives some audio from waves, and we're no different. We pick up some signal or just give off our own signal, and we're basically antenna ground systems too, only biological circuitry instead of like hardware circuits.
It's amazing, isn't it, how it interconnects and makes sense. I don't know if people have thought about that before, comparing yourself to technology, but we have to explore this past, this is what the construct's doing, so everything within it is under its laws, isn't it?
And we didn't invent it. Things like you go on vacation to ground yourself out, etc. We didn't invent those terms. They're really coming from way back. Yeah,
they have to be done if them to exist.
Yeah.
Yeah, that's what we're finding, isn't it? All these myths and legends are actually turning out to be reality.
Yeah. Pretty much. They just got forgot for a time.
Yeah, that's the problem, yeah. We forgot people, but we're getting it back. We're getting there.
Yeah.
It's making more and more sense the more we look at it.
Here are some of the brain signals at different states. In theory, I don't know how mine bounce around and stuff at different times, but they got squiggly lines that say, oh, if you're awake, you have squiggly lines like the red one on top, and if you're relaxed and not thinking, well, you got the brown wave, whatever, they can have their fun, bunch of waves.
Frequencies and wavelengths is what we're looking at, isn't it?
Yeah, but these waves are being generated from probably the outside, Stress is an external stimulation. If you're in deep relaxation and stuff, you don't have external stimulation and other things to disturb you, right?
Yeah, we have to be, I do think we're in sync with this construct. We have to be, where all these waveforms are coming from.
Yeah. So if you're having a heart attack, don't listen to rock music,
if these waveforms didn't exist, I don't think we'd be living.
No, we're a waveform ourselves, in a sense, so we all have our specific frequency we function at.
Yeah.
Here's for your sense of smell. You don't actually have chemicals that go all the way up to your brain. It can only send a electrical signal, So we're stuck. It's like when we see with our eyes. We're not really seeing the scene that our eyes and our retina is picking up. It's being converted and sent to the brain and interpreted.
Yeah.
Same as a sense of smell, hearing.
Yeah, we're a big receiver transmitter, aren't we?
Yeah. Our signals too, like the color, the vision we have, the audio, when they combine and go to the brain, they're a lot like a signal that's transmitted for radio broadcasting and television. They have a composite video signal that has audio and video, and we have that too. You open your eyes and ears and you're producing a composite video signal. And they're similar. They look alike physically, on an oscilloscope. There are slight differences, but not much.
Yeah, you put a robot beside that, and how man's made a robot kind of emulate that. And it's, like you say, it's technology and processing of signals and things. It's no different whatsoever, is it? You could probably manipulate them signals and make something that doesn't taste very nice taste nice.
Oh yeah, it's definitely. You can stimulate your sense of smell with electronics, radio frequencies.
Mm. Yeah.
If they can get to the brain and stimulate the brain where the actual smell would have stimulated it, it'll trigger it, and you'll smell roses or toast or whatever the case may be.
Mm-hmm. Makes sense to me.
Well, they actually have a thing in Montreal they did where they put these sensors on a person's tongue and, put blindfolds on them and stuff. And eventually they're able to see with their tongue the electrical signals coming off the transducers or the photosensors would send the electric signal to the tongue, and the tongue sent it to the brain, and the brain was able to route it and interpret it as,
a video signal.
A video signal, absolutely, from the tongue.
Oh, wow. Yeah, that's a breakthrough, that, isn't it?
Yeah. It might explain how some fish and other stuff see in the dark.
Yeah.
They might see through their tongues too. Who knows?
Taste the dark. Yeah, you look at some of these species of creatures out there, and you think, what can they process?
Well, I think we used to say all the time that most animals see in black and white and all this nonsense, but there's so much color in fish and birds and everything out there that it's ridiculous to think that they only see in black and white or shades of gray.
Yeah.
That don't make sense, I just don't get why you'd be colorful and have color and be colorblind.
And know which color to be to scare a predator off as well.
Yeah, tell that to an octopus that can mimic any background and millions of colors,
Yeah.
Texture,
Yeah.
Should only work for NASA.
There's something you've taught me again, Jim. I didn't know that,
Yeah, one thing I was thinking too is some of these new nebula shots and stuff. You put cream in water with a black background, and just the right dilution, you got that sort of like creamy background with lights that they're offering us now. Anyway, I just wanted to kick James West Satellite, whatever, in the teeth there. Moving right along.
Right, here we go.
No, well, apparently we have different signals when our eyes are open as opposed to closed, and that makes sense too, because.
Yeah, something send the signal for it to close your eyes, isn't it?
When they say asynchronous, it means it can flow both ways at the same time. Or, okay, asynchronous. One way at a time, I think. I forgot what asynchronous means.
Not to worry. Synchronous and asynchronous. But it will make sense, and it's all down to signals being sent, isn't it?
Yeah, low voltage beta rhythm when the eyes are opened. And it's, I guess, always good to know. You never know when you'll need that, you know.
Yeah.
In a dark cave. I remember one time I read that low voltage beta rhythms when the eyes are open. I'm moving right along. Took note of it. Well, here, if you drink a cup of coffee, you'll dilate your lenses. But yeah, the optic nerve, again, we get an image from the retina as an electric signal. It's sent as a, you know, chroma burst or a color burst and signaled to the brain, and it's interpreted, you know. It has to be scanned out and spread into a medium just like a TV would to draw its own picture. And it draws a picture on these materials.
I was just looking at the cones there, Jim, behind the eyes there, and how it makes an equal and opposite image. You know, the cones, that's not much different to the angels, is it? The angels' cones are, you know, creating images, but...
Yeah, almost like, upside down, yeah.
Yeah, it's flipped upside down, isn't it?
Yeah, because of the lensing effect. Yeah, that's why we look at our sun and the moon. We might actually be seeing them upside down, you know.
Yeah.
These basically reversed like you would in a mirror.
Yeah, we wouldn't know yet, would we? But it would make
That's
sense.
a more decent looking brain.
Yeah, the last one looked a bit well abused, didn't it? The other one.
Yeah.
This looks in good condition.
Someone painted the town with it. Painted it red, I guess. Yeah, even the eyeball don't look too bad here.
So that's your video in, guys. You know, there's your video input to the brain, isn't it?
Yeah, just like a camera would send it to a little chip and send the signals to red and blue or whatever receivers. And, you know.
Hey, also the cool thing is, as they introduce new technology like 4K, your eye is actually able to distinguish all of that. You know, what is its capability? How many K can your eye actually see in a one?
Don't know.
Yeah, I don't think anyone knows that yet, do they? Because we haven't got the technology.
Like, you know, you see in Predator the different, you know, zoop, 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 we're seeing in ultraviolet, infrared and stuff. You know, our eyes don't do that, although we can see for sharpness, detail, tone, color.
Yeah.
You know,
we need aid to do anything else, you know, like technology to look beyond, to take it beyond our visual range. Yeah.
Yeah.
Here we go.
That's supposed to be the range for vision of these frequencies and stuff. Some of these would go to the cones, some would go to the rods, signals from either or either.
They've totally reverse engineered the human, haven't they? To know all this.
Humans, moose, deer, cows.
Yeah.
Because, you know, all the eyes have the same basic idea. All the ears have the same basic, you know. It's, how do they say it, you know, same stuff, different pile.
Yeah, yeah. Same stuff, different species.
Yeah.
Ooh.
And that's the basic LC circuit, is a capacitor and a coil of wire, basically. And what's nice is that no matter what, it's able to resonate. It can take radio frequency out of the air and actually develop a charge, or with enough time you could actually charge a battery with a circuit like this.
Yeah. And you look at the positives and negatives there, it's no different from the ground and the positives, you know, going on in the ether.
Going up, yeah. And
like a capacitor kind of configuration, that.
We have to insulate and isolate all this for any of it to work. It can't ground out or it fails.
Yeah. Doesn't that make sense, people? You guys in the chat there.
when it gets too high, there's a lightning discharge. Same here with this little circuit as out in the environment, you know.
Yeah, that's right. That's why, like, you've been on Jimbo, you know, you can teach these people electronics, all this information that they, you know, probably never thought of before. You know, do we know that? Do we need to know this information? Yes, I think we do, because we should be harnessing this information. Our ancestors used to.
Our whole world is about resonance and basically magnetism and stuff. You know, people think that there's gravity. I think there's electromagnetism has 10,000 times more force. You know, you take a 7-8 gram balloon, give it a little static, and it'll stick to the wall overnight. You know, where's gravity on vacation? You know. So.
Jason did do a good decode of gravity. I can't remember which video it's in now, but there is one. It's in our. I forgot the name of the video now. But yeah, it is, you know, Jason has covered that and do something else. Oh, E equals MC square. So you've got to, you know, give the APM perspective on it. So we've got that somewhere in an older video. If people want, you know, you want to understand about gravity, have a look at Jason's explanation that factors in the APM research decode.
I need about a 5-minute break.
Yeah. Okay, Jim.
I'll be right back there. Give me a few minutes.
Yeah. No worries. I'll interact with the chatters. Hello, chatters. Who's in? Hello, Lisa. Hello, Anne, if you're still there. I don't know if people are still here or not. We get carried away talking on the panel. Claire. Hello, Claire. Hello, Heaven. Yeah, Jimbo can melt your brain easy. Very knowledgeable guy, Jimbo. An asset to the team. They're all assets, you know. All these people in this team are assets. And we've got the right skill sets needed to bring this out into the open more, to explain it. And they're good friends and a very good bunch of people. And none of them come with ego. Jimbo's been here forever in flat Earth. You know, all Jimbo's ever done is give people good advice or how to word things correctly. He's always been here to help people. That's what I like about Jimbo. He'll give you the better terminology, so you know, so you don't look like an idiot when you're trying to explain it. Jimbo's always on hand to help you word things better. You know, some of my terminology comes from knowledge Jimbo taught me, because I didn't know the terminology to give some of the, you know, the words to give some of this. So I've had help off Jimbo, I've had help off Jason on, you know, just on the terminology side of it. That's a unique thing about our team. You know, we all interact with each other and help each other. You know, we'll all help each other explain different parts of this, so we all get a better understanding of it. The largest angel. Good question. I would say it's the one, the reactor at the center of the grid, that is connected to everything else. And well, that's the heart of an angel. All comes from and returns to the one, Walter Russell. The one he's referring to, I think, is the one at 0.0. Below the center of our map. Giza is not the center, no. It's in the Atlantic. Look at our map and grid, and where we've got the center of our grid, that's where 0.0 is. It's near Ascension Island in the Atlantic. Now, people go for the Giza option because they think, you know, the pyramid is something special, but it's not the center. It's actually a fusion reactor. If you look at our 144,000 video, it's a fusion reactor. It's what's below there that's actually special. I mean, that is special. You know, a fusion reactor is special. This is technology, the creator's science is what it is. It's using the science of the creator. So what we're calling fusion reactors already existed. Well, they could put the grid in 3D. You know, it's in 3D. The grid we're using is a 6-tier pyramid. So there's layers below the ground that's got technology on inside that's creating what we call our world. We don't know how deep it goes. We don't know what actual shape it is. I don't think anyone knows. Who said there's an edge? We're not saying there's an edge. We can see our research takes you over the international date lines and the North and South treaties. This world's larger than they're telling us. AI, well, we've discussed AI before in our team. We can't get an end point on it without exploration, really. But, it doesn't mean we throw it away. As Mauro Biglino did talk about robots. Now, are these AI-type robots? Are they just automated robots? He didn't actually say. So, it's on the APM shelf, the AI being involved. But, even artificial intelligence, that had to be created by someone. It doesn't create itself. So the creator, if the creator's angels or these robots or whatever's down in the underworld, they might actually have artificial intelligence. It would make sense to me to use technology, for long term. It would be a piece of technology and not a living being, because a living being comes with a lifespan, whereas a technology, especially on these kind of designs that seem to last forever, would probably run forever. So, we haven't thrown AI out the window, but we're not saying it is AI either, because we don't know. Without exploration, we can't really go deeper on that. You would have to go and explore this world and find out what's there and, work out how it works, which is probably what these people are doing. Maybe that's where they got the ideas from. More than likely is. Yeah, they do have field experiments, obviously. They're still learning. They're still playing around with this technology and probably trying to see, what they can do with it. Jamie Robbins thinks the creator created more than our world. Yeah, we don't know what's beyond here, do we? This might be part of something even bigger. How far out does it extend? But, from what we're seeing, it goes out in all directions. So they're having the time of their lives exploring it and doing things, and we're just spinning through space on a meaningless ball, apparently. Yeah, right. Pull the other one. So I hope you're enjoying what Jimbo's teaching you now as well, how this technology actually relates very close to human anatomy. I don't think they can fully control the angels' heaven, but what they're doing with chems is interfering with them working and revealing themselves pretty much. But who knows, what they do? We've no idea what they're doing down there. We have no idea to what extent what knowledge they have on this technology. It's going to be way ahead of what we're talking about. We know that. They've had hundreds of years head start on this, it seems. This has been going on for some time. And the attempts that they've done, the length and ways that they tried to hide this, everywhere possible they've tried the way to hide it or explain it away as being insignificant. Well, it's not. It's something very special and sacred. I was watching a video where a guy was bragging about commanding 10,000 angels, commanding the power of God. Yeah. He's worded that correctly then. The demiurge is so complex too. Well, it's electromagnetism, Jamie. Eve, the larger halo's got a right-hand rule, and Adam, the smaller halo's got a left-hand rule. And when they're both running, because one's electric and one's magnetic, it causes its poles to extend, spiral upwards kind of thing. You know, if you watch the Adam and Eve decode, it creates the torus field. The torus field gets created because you know, electricity's got no choice but to be elevated 90 degrees in opposition to Eve. So that's what's elevating things into the sky, including a mirror image of itself, of its own halo. The demiurge is a mirror image of the physical one below. You're seeing a projection of the one below, which does have a reverse flow to the one below. So that's why you end up with two cones, one going up and one coming down. So that's the Holy Trinity of nodes 1, 2, and 8 on the halos. Well, the 144,000 number we're using is just a guide. You know, that's a start number for how many angels there actually are. When you listen to the Book of Enoch, he mentions hundreds and hundreds of thousands. So we haven't actually got a number. So we thought 144,000 is a good start. You know, it may go beyond that.
Yeah, instead of one big one, there's a bunch of small ones.
Yeah, it can come in various sizes.
Even, yeah. Yeah, and depths.
Yeah.
Different purposes.
Different roles, different configurations, different cycles. Oh, classes, sorry. Yeah, he's asking how many angel classes there are. Yeah, so, yeah, you know, we're going to try and go through that. When you look at how they've named the saints, you'll find there's lots of saints repeating. So to us, that's that does the same role as the one in where the other one was. So if you find like two St. Pauls, they're obviously the same configuration of angel. So a good way of determining if there's different ones is looking at how many different saints there is. There's a good way of finding.
And what they're the saints of, because you have saints of travel, saints of,
yeah,
of every nature.
Yeah, you know, what the stories tell you about these saints will give you an idea of what its function is. Yeah, it's a good way of putting it, Jimbo, isn't it?
Mm.
It'll tell you its functions and roles. Anyway, should we continue with these images?
Yeah.
Yeah, we're on to this one here.
To mention that everything has to be like sort of AC and then clipped to a DC. AC is the driving force, and it allows things to modify it and use it, all kinds of waves out there, including like AM radio waves, and a really simple circuit with no battery, nothing, just a simple what we call antenna ground system, a little coil and a little piece of wire and ground to a kitchen sink, and you can pick up radio signals, So,
yeah, you look at the coil, people, it's just a spiral. Look at it.
Yeah.
So even in technology, they're using the spiral.
This spiral gives off a magnetic field around it, lines of flux. And they're used very often in electronics and in, engineering.
Yeah.
But it's repeating what at a microscopic level or atomic level is happening. And we're just repeating it on a slightly larger scale. More primitive.
Yeah. But it works.
It does work, yeah.
We get there. Here we go.
Here, again, we have an antenna ground system and a rocker system. And here they're basically wanting to show that the current and voltage can lead and lag each other, depending on their phase,
Yeah.
when they actually come into being. So that's what we got there in this image. That's just a little technical shit there.
So, the components are just trying to manipulate the waveforms to work how they want it to.
Yeah, and the green is the current, and it's almost always out of phase with the voltage.
Yeah. Hope you're understanding this, people, how it all factors into it. These waveforms here, they're pretty much like the ones that we see over the map.
Yeah, here it's showing the discharge of both the capacitor and the inductor, the L and the C. Pretty neat.
Yeah.
Simplified, but still okay.
Moving on.
Yeah. Now, the wire gauges there. This doesn't really do it honor because the triple aught, the 4.0 and stuff, you can't fit your hand around it, you know. So the cables may appear larger than they are in this little mirror here. But they do show what they call what is that? Like the Hindi tiles and stuff there. What do they call them? Mosaics. Sacred geometry.
Yeah.
You know,
the sacred geometry. You can see it going down the middle there.
Yeah. And it just repeats in size as you expand, eh?
Yeah, so for the people wondering why they're using different thicknesses of wire, it's just to get more power through, really, isn't it?
Yeah, and note the twist too for the right and left hand rule there. They can't get around spiraling the wire in the cables.
Yeah, that's the difference between AC and DC, wasn't it? They could only send DC so far, couldn't they? And then you're getting fires and problems being caused, the substations.
Well, the thing about AC and DC is that AC it has a negative half cycle, which is like negative power, right? Where DC is continually, able to heat every wire has an amount of resistance. So when you pass AC through it, more electricity goes through than DC. Because again, the DC faces more resistance.
And so something we should make them aware of as well. What they call electrons flowing is nonsense. What's flowing really is a waveform that's agitating already pre-assembled positives and negatives that reside in these wires from manufacture. Yeah, so they have to, because they're under the laws of this construct. So when we make something, it automatically aligns everything that's that's metallic or conductive. It will, all the positives and negatives inside it are aligned correctly.
It rocks.
There's a song, people. Here we go, rocking all over the world. Yeah,
a rocker circuit. It's all rocker circuits. Rain, evaporating water falling back as rain is a rocker circuit, basically.
Yeah.
A rocking action, back and forth like a swing.
An equal and opposite effect.
Lake, evaporation, rain, lake, and it just goes on and on.
The rockers, people, has a good word.
Rocker circuits.
It's funny that, isn't it? Even in human life, we have like mods and rockers. There's always an equal and opposite of some kind, isn't there?
Well, the term rocker was around long before even, rock and roll and stuff,
Yeah. Strange, you look at the words they used.
Yeah, and people becoming, I was petrified,
Yeah.
That's from the time of and I don't know who there. Yeah, here's a nice little battery charging circuit with a bridge rectifier, a source of power in, and a circuit protector Zener diode in gold.
Yeah, can we elaborate more on that bridge rectifier, Jim? Because
what it does is it'll allow electricity to pass in the direction of the arrow. But if for any reason more electricity or voltage develops on the opposite side and causes a reverse avalanche, it breaks the circuit and protects the battery. So it's acting as a circuit breaker or as a fuse.
Yeah, so and also if you remember, people, that was what I showed of the solar panel, the day and night polarity switch. We can get into clipping waves there, Jim, can't we?
Yep, absolutely. This is basically a wave clipper. You have AC in at 250 volts and 50 hertz. It's a European guy, I guess, this one. And right to a bridge rectifier, right? So that's clipping the waves. Your full AC is not going through. No AC is getting through.
Only what it wants to, only what it allows, yeah. So very important bit of kit, that, isn't it, that bridge rectifier?
Yeah. And there's hardly any radio equipment or anything that doesn't have one at the power supply, at the power source.
And this is something I noticed there was a guy that was plugging solar panels in on his channel and directly powering power tools, but he found some worked and some didn't. And the some that didn't, people commenting, some of them use a half-wave rectifier and this, that, and the other, which would actually make sense now, doesn't it?
Yeah, well, the half wave only gives half the power.
Yeah, so that's why it wasn't working. It's only giving it half the power it needs. So if you put a full bridge in there, it would work, wouldn't it?
Probably would, yeah. And depending on the capacitance too, you need a certain strength of capacitor.
Yeah. Yeah, you'd have to upgrade a few components, wouldn't you?
Yeah.
But yeah, that makes so much more sense now why some things worked and some didn't, because it's working in half waves and full waves, isn't it?
Yeah, big difference. A lot of cheap phone chargers are half-wave chargers. They take hours,
So if you want lots of power, obviously you're best using the full wave bridge then.
Yeah, about 2 amps at 5 volts.
That makes sense. Yeah.
Yeah.
And somewhere else I was going to mention this bridge rectifier. If you remember the cross plate on the center of our grid, Jim, that reminds me of a bridge wave rectifier. Now
it looks a lot like it, doesn't it? Eh?
It does. Remember the piece that crossed over into Greenland that you took a screenshot of? That's that plate in the center of our grid.
Yeah, pretty much. Because again, where two metals plates interface, there's a junction. And we call them junction diodes, So
yeah.
Any two metal plates that reside next to each other or on top of each other, there's an interface and there's a junction. You got your diode right there.
Right. So now we know the configuration on the grid that we're using over the map. What we've got in the center there, the center of that full bridge rectifier on our grid, we've got the heart of a motor which would produce electric.
Yeah, pretty much, yeah.
So it's in the right place for it to distribute it then, isn't it?
Yeah. Because you can charge with static, with air motion, water motion, any number of things can help to,
Yeah, we'll have to
go through a rectifier system.
We'll have to look deeper into that configuration and on the center plate, because I can't stop looking at that full wave rectifier, and it's exactly what it's reminding me of. And it makes sense to be there, wouldn't it? Right, the heart of it.
It would, and it's got the right shape too,
Yeah. Amazing stuff. Funny how all this thought, comes together just looking at components.
Well,
look at the LED there as well. There's a cone shape there, designed to the signal goes one way. Showing it's coming down, isn't it?
That the so-called electron flow is that direction,
yeah. Too easy. Ooh, here we go.
This is
input.
This is a schematic of an old TV, black and white Toshiba, and it represents just like the antenna ground system, just beautifully and stuff. But we take in signals very much like the antenna of this receiver does, and process it very much like the circuits in this diagram here,
Yeah, so we can start looking through this and start pulling bits out from reality, can't we?
Yeah, we could see the bridge rectifier as being our digestive system, our oxygen intake, whatever, and our fuel.
It could be our solar plexus, couldn't it? Our solar plexus, Jim.
All we know.
It's power energy distribution, isn't it?
But this, in a sense, is a mimic of, except for the television and the well, not even, I can't say that, but this is basically built a representation of what we are and how we're built and how we process signals. The same basic layout plan, simplified,
And there's a center plate there, see it? Full of the bridge. It's like our center plate on the grid.
And you just need a few coils to power it.
Yeah. What else we got in here that we can prod around with? What catches your eye, Jim, on this?
Well, the tuners, all they're sending in is magnetic waves. There's no physical contact between them and the rest of the circuitry, which is pretty amazing,
Mm-hmm.
These old TVs, you would actually have to tune them with a knife or a flat screwdriver.
Yeah.
The old tuners, channel selectors, had wire, sometimes in coil, sometimes just a length, and by moving it closer to the center of the selector. You change the capacitance and change the tuning. So you tune it with a hammer and a knife, you know, basically.
Yeah. Well, what's amazing, you know, looking at this, we're not operating very much differently ourselves.
No. Even in the frequency.
You know, what all this is doing, we can process in a split second. You know, our own brains processing all of this so easily.
Yeah. And the audio is simplified just like it is for us, you know. Our audio is probably the least complicated of our senses, you know.
So, you know, schematic diagrams, people, you know, you're looking at these and to us, it's like looking at human anatomy now. And the angel technology, you know, the macro and the micro, isn't it? We're looking at the macro and the micro in one here.
Yeah, there's a way of laying this out with the map, like the Sears map or whatever there, and, you know, plotting out the metals and stuff and plot the sun and its basic circuitry, you know.
Yeah, well, you know, this is going to have wave guides in. There's your horizontal and vertical hold, you know, things like that, you know.
And deflection yokes.
Vertical hold right there.
Yeah, and horizontal and vertical deflection.
Vertical line, yeah. So, you know, vertical cut. It's even cutting the vertical off here. Deflection yoke. Yeah, you know, the world chakras to us are like wave guides, and obviously they're clipping the waves as well then. Yeah.
Like in the yokes, they're drawn side by side, but it'd just be too complicated to try to draw them over top of each other.
Yeah, yeah.
So,
one horizontal, one vertical.
Yeah. Well, you take two, and you can control the east-west, and two, and you can control the north-south.
Yeah. Horizontal and vertical hold right there. You know, that's what's keeping... That's kind of, when you think about it, that's kind of what's keeping the sun between the tropics of Cancer and Capricorn.
And it's just adjusting the amount of voltage going through any point in the coils, you know.
Yeah.
That coil is giving off the cone, you know. The sun's riding along. Basically.
Ooh, you get lost in here, couldn't you, decoding all this?
Oh, yeah, but, you know, you get used to the signals and separators and, you know, the timing circuits in there. Because once it gets to the one side of the screen, if you will, the horizontal flyback killer, trace killer kicks in. It jumps back without tracing on the screen.
That's what Luca was asking me about the flyback killer before, because it's not a term he was familiar with. You know, he's a guy in Italy, and he asked me to explain it. So give him your explanation of what he's doing. You know, the sun.
When it gets to the farthest point that it can, it gets shut off and it just moved right back to its starting point, or 11 miles north of its last start of day.
Yeah, so a quick decode of that is the sun traveling west, it's shut down, it's light suppressed, it returns east as quick as possible to start sunrise the next morning again.
Yeah.
Yep.
It's sort of like the process of the TV and scanning lines from top right to bottom left, top right to bottom left, you know?
Yeah. So when you look at technology like this, people, you know, this is created from the knowledge of the realm and the understanding of human anatomy, you know, when you look at this, isn't it?
Oh, yeah. Yeah. There's nothing new under the sun, you know.
No,
and even our modern gadgets like this iPad, it's just, you know, this with color and with a transmitter and receiver, you know.
It's like those old sigils videos we looked at, Jim. Remember we were looking at them, and they were just more technological configurations that we were decoding, weren't they?
Mm-hmm.
More schematic diagrams of certain processes.
Yeah.
Not much different to this, really.
No, all grounded systems. Really no different.
And you can even see what looks like to be, the waveforms down here. See that? Looks like a square wave, and this one's becoming a spiral.
Yeah, so often square waves like that will be used for synchronization and timing circuits.
Ah.
Sometimes 3 waves are enough to trigger a circuit or a switch somewhere. like the flyback.
What does this P stand for again, Jim?
Point to point. Every
to point.
wave on a sinus dial or amplitude wave.
Yeah.
Measure between two peaks, and it's the peak to peak value is 14.
Is that so it can clip it if it was beyond it? Is it?
If we clip it, we use rectifiers, and we would. Just a second, I've got a brain fart there. We clip it, and then a certain number of waves would trigger a certain voltage in a capacitor or something, and that would be enough charge to, engage the relay or trigger the horizontal flyback or do whatever,
Yeah. So yeah, it's all by design, and everything's by design.
Yeah.
Yeah. Really is nothing new under the sun when you understand this.
Yeah. And with the transistors, they always work where a signal is applied to the base and it comes out the emitter, and that one is sent to the base of the next one. It's called cascade amplification and stuff, so even when you see a transistor, usually it's to amplify the current or the signal strength.
Yeah.
No strength. It don't take many. Often 3 is enough for a lot of boost in signal strength.
Yeah, really useful things on transistors. Remember that video I was showing you with the induction coil.
Yeah.
Yeah, a lot of useful projects you can bring these transistors into, isn't there?
Oh, yeah. And if you had to, you could use them as diodes if you wanted. You just wire them in as a diode.
Yeah, there's a surprise there how you can use them as different things, these components there.
Yeah.
They've got like lots of uses.
Yeah, if you don't have a diode and you have a bunch of old transistors, you can just wire one in.
Hey, when you get sorted back at home, Jim, you set up again, you should maybe start some of these electronic courses and show people how to make make some things that are useful.
Components, no integrated circuits. They hide too much.
Yeah.
Yeah.
Well, they make it look confusing, and it's not really when you break it down, is it?
No, and you put together simple stuff like flashlights first, and then simple AM radio. You build a little AM radio that doesn't even take a battery.
Yeah.
You grab it out to your kitchen sink, and you get to listen to music. Hey, pretty cool.
All right, let's jump to the next one.
Yeah, this is just a high-frequency tuner, basically. It shows a UHF socket for signal input, and then the circuits that are going to amplify it as it goes out towards the TV for output of sound and picture. But it's just cute. I liked it. I forget why I threw it in there.
Yeah, it's a nice circuit, though.
Yeah. And here's just a basic circuit where R is a resistor in this. It could be, a filament to a flashlight or any number of things,
Yeah.
A little LED readout for a number, a fob, could be anything. The resistor is anything that resists the flow of the current and voltage.
So you just basically throttling it to get the voltage you actually need, then, yeah?
Yeah. And protecting other components that take very little, like diodes.
Yeah.
Milliamps. So if you hooked them to a battery directly like this, you'd fry them. You have to go through a resistor.
Yeah. Yeah, I've seen that happen a few times.
Yeah. Oh yeah. And again, if you take a clear LED, wire it in backwards, it becomes a photocharger. A cell that can actually capture a photon, if you will, and turn it back into electricity.
Yeah, I've seen something about that. Yeah, so, these are projects we need to look at, Jim, isn't it? And expand on them.
It just, wired in reverse, has a different purpose.
I'm looking forward to them kind of projects, I am.
Yeah, here are just some of the basic symbols you've been seeing throughout this, you know. A few are new, but they're all pretty self-explanatory.
And, you know, take it from me, people watching, you don't need to know anything about any of this to follow projects to make your own, you know, your own electronic equipment. There's plenty of people online show you how to make things. They'll show you the components you need.
How to sell stuff.
Yeah, you know, and it will work. And you don't need any knowledge whatsoever on these components. You know, it will work. And
instead of paying $200 for a metal detector, you can actually build a real good one for $40, $50 in parts and scrap.
Yeah, yeah.
You know, you can use an old Frisbee as a disc for your wire coil, you know, and just move on from there, you know.
Yeah.
Broom handles for your pod, whatever.
Put the frequencies in you want it to scan, and off you go.
Yeah. Oh, yeah. And you can make it as sophisticated as you want, you know.
Yeah, discriminate things out.
Yeah, because you make it, you can make an alarm system that's not as disturbing as some of them have. Because, you know, everyone for a mile around will know you're detecting, or it's like, say, come get me, you know, and maybe, you know, it's almost embarrassing. Because you like to be discreet a bit, you know.
Yeah, best use headphones out of it.
Yeah. And there's a little power supply. I threw that in there because, well, it looked nice. There's no swollen capacitors. Nothing looks burnt or cooked or fried. And it would probably work if you hooked it up and used it. And that's out of, I forget what, but TV.
Yeah, I think it was for a monitor, this, or something, wasn't it?
Yeah.
We'll see the image. Yeah. And that's all you need to power a screen, people. You know, look at the configurations and how it uses capacitors to store energy.
Yeah, it hasn't changed. And capacitors today, they're of lesser quality than they were 10 years ago. When, you know, they use a cheaper oil in some of them that have oil, and they use thinner plastic with a thinner layer of metal on it.
So it's worth scavenging the old stuff, then, isn't it? Yeah,
absolutely, definitely. You know,
don't chuck old electronics out, people. Have a look inside and see if there's anything worth salvaging there, because you're probably going to need some of this in the future.
Yeah, you can get magnets and stuff out of VCRs, or not VCRs, but the microwaves, old hard drives, whatever. You can salvage, you know, a lot of components.
Yeah, I showed Jimbo one at 12-volt induction coil that someone made, and really? When that one I showed you, Jim, and straight away I was thinking of uses for it in an off-grid situation for like heating water and things, and then, you know, in my mind I was elaborating on what you would need to add to, like, you know, control it so it's not too hot all the time, you know, have it automatically shut down when it gets to a certain temperature. You know, you can do all this with components.
Yeah, that was exceptional use of recycled stuff.
Yeah, you know, what we can do maybe is show that one day and then take it further. You know, I forget. You know, I've used them before on an old project I made. I made a solar heater. You know, it just takes the sun, it heats it up, and when it got to a certain temperature, I can't remember what the component was, but it got to a certain temperature, and then it would switch the fan on to allow the heat to get blown into your room. So, you know, it waited till it got to a certain temperature. I forget what the component was called, but it was like, you know, it gets it's obviously set to trigger it at a certain temperature.
Here we have ambient temperature sensors that are outside and placed in a place where the temperature is supposed to, in theory, stay about average.
So what I done with it was, you know, I bought the one, and I thought, well, you don't want it blowing cold air in, so I thought I'll buy a component that waits till it gets to about 20 degrees, and then it starts switching the fan on to start blowing the warmer air in, and it worked, you know.
Right.
In the winter, it was just a small solar panel, and heat, you know, the sun shining on. I think I used I got, you know, all the beer cans and cut them up, flattened them, and put them in this box and sprayed them matte black, so, you know, it absorbed the heat. So it was a free heater, really, for, you know, so you can take heat from outside and put it into your home.
That's right.
and it was all controlled by a solar panel that powered fans, you know, through components switching on when it got to certain temperatures, or switching off if it got too hot. So in the winter, you know, it was outputting somewhere around, I think it was about 37 degrees centigrade, which isn't bad for winter, is it?
Oh, that's pretty good.
Yeah, it's nice and warm. You know, it works. It works. I actually gave my mother one. She complained, and she said, I come round one day, she says, you'll have to have a look at that. It's not working. I says, why isn't it working? She said, well, it's still blowing hot air out. Well, you know, it's the middle of summer. She says, you know, you only use it in winter. But she was using it in the summer, wondering why it's blowing hot air out. No, it's a, you know, it was a winter one to warm your house up in winter for free. So, you know, these kind of projects I would like to see brought into our research and get people, you know, playing around with this stuff. It's, it'll get your bills down. It's interesting stuff. It's related to how the construct works, and it'll give you a good idea. You know, you can teach your kids this, and by the time they grow up, they're going to be, you know, electronic experts, I would have thought, you know, just by playing and learning from an early age, learning all this.
Well, I really have this big faith in a thing called the Arduinos, these little circuit boards. They allow you so far and so fast, it's just mind-boggling, you know. And then you can get into programming if you want a little bit, Python or C. Just an amazing way to get into it, you know. Yeah. But 101 electronics kit isn't bad either.
Yeah, we'll definitely cover more of these kind of topics. Is this the last image, this one? I can't remember.
Maybe not.
Yeah, it was. So there we go on the electronics presentation from Jim. Nice presentation, Jim, and thanks for taking us deeper into how the components work and stuff.
Well, hopefully we'll be at a point where, you know, we can just, you know, talk and answer questions from the people in the chat and stuff, and
yeah, let's
stay on one track with this, you know.
Yeah, you know, they're asking chat there where to begin learning these things. Well, you know, we hopefully what we'll do is me and Jimbo will get a project going that we'll present it on here and show you how to do it yourself. I actually done one in an older screen where you could use a solar panel and a phone battery to, you know, it'll charge you up during the day, not night, and it automatically switches LED lights on. And it, you know, the thing runs all night.
Basic electronics and basic radio, you know, AM radio.
Yeah, it depends how deep you want to go, Heaven. You know, you can follow people's tutorials online. You know, we can give you links to some good channels that we've been watching.
And it's cheap, you know. All it takes is a soldering iron, some solder, and salvage stuff, you know.
And if you haven't got a soldering iron, you can use a heater, lighter, and, you know, a bit of wire. That's it. That's all you need, really. There's always a way of, you know, making things work. These are kind of, you know, these are what you would call life hacks, really, isn't it? You know, life hacks that you should learn.
Well, you know, when they had like HBO and stuff, and they were scrambling signals, it was people, and you know, not even 24 hours they hacked the HBO signal, you know.
Yeah.
So, and they did it with aluminum foil and a piece of cable, which was pretty amazing. How they figured it out, I don't know. But they understood phases and other stuff, and they made the thing unscramble. And it didn't take a day it took them millions of dollars to do the scramble at that company, and just a day for a hacker to, you know, say it's all worth nothing. Oh well.
Yeah, it happens.
Yeah. People were more interested in descrambling the Playboy channel.
That's what happens, isn't it?
Yeah, and they did. And then at one point, a Max Hedron type person took over. There you go. Here, let me mute. I'm going to go down for a cigarette.
Yeah, okay, Jim. I'll interact with the chatters, see what's taking place. You're just catching the end of this. Yeah, you know, Jimbo's presenting electronics into the APM research and showing you how it actually, you know, pretty much relates to human anatomy, the way it works, and the construct, how it works. Humans and technology always seem to go together. Any recommended books? I'm no expert on it, Heaven. Jimbo might know some. He's just gone for a cigarette and then he'll be back. You know, what I'm saying is, you know, you can follow some channels online and get, you know, salvage some components from somewhere, or even buy them from the local shop or eBay and make some of these, you know, experiment. Have a look at what they make and see if it's any use to you. You know, like a battery charger or lights that switch on automatic at night. You know, you can use salvaged components to make these things. I'll find the one that I made. Because you know, I did make a circuit diagram for it, and it came from a channel called Big Clive. Which screen was that in? It's in one of our streams. Oh, there it is. I found it. So I'll put that on the screen, and you can have a little look. You know, this was a project I followed online just to make one of these myself. When I was looking, you know, I decoded that there's a polarity switch between day and night, so I was trying to figure out a way to prove that or utilize it. So I was detecting 1.9 volts still at night time, and that was enough to cause the motor on my air pump to reverse polarity and become a water pump. It was actually running in reverse, and that's when I realized, you know, there's power there at night we should be utilizing. So I'll just, there it is. I'll screen share this. You may have seen it, I don't know, but maybe other people haven't. That's the one. I'll share that and I'll just leave it playing and talk you through it. Yeah, that's on, yeah. So, you know, this was my air pump, which I found at night time was doing a reverse roll. The polarity switch caused it to reverse the flow at night. That's what happened to this air pump. And that's when, you know, I realized there's things at night going on that we need to be harnessing and stuff. So I found this circuit on bigclives.com, this guy here, and I thought, oh, I'll follow that project. This one here, an old phone battery, a little solar panel, which I had plenty of them lying around, a few components, and you were pretty much in business. And this is the one I made, and this is Mama Angel testing it. You know, come night time it'll switch on. During the day it's harvesting and storing the energy in that battery on it. It was just an experiment, you know, to see if it's utilizing this voltage at night, because, you know, according to Big Clive, the circuit he made, most people think it's a leak. They call it a leak, this night voltage, but it's not a leak. It's actually a polarity switch that Realm undertakes. So any of you guys out there that, you know, think it's a leak, it's not a leak. There is a definite switch in polarity between day and night. And Big Clive said this circuit takes advantage of any, you know, this leak, which would be the voltage it's generating at night. And this is a schematic I made of it, of, you know, what's on the back of that solar panel. I made the battery, the components that are on it. So, you know, you can go to Big Clive's channel and just copy what he did yourself, and you'll make one of these. You know, I know some of these components anyway. So I like these kind of projects. You know, you can take them further, you can expand on them, make them bigger, make them run your home even. And this one here, you know, there's another little experiment making a battery level indicator. You just press a button and it'll tell you how much charge is in that the battery. I put a button, you know, the momentary tactile switch. I added that because I found if you wire it direct, these lights are always on and it's just going to drain the battery. So you only press the button when you want to check it. So, you know, I added that circuit to the original one, so expanded on it a bit more. It's not essential, but I thought, oh, you know, it looks something nice to make, and it was just cheap, easy components, so I made one. And that was just to show you people, you know, you could teach your kids to learn your kids how to do this, or learn it yourself. Male, female, doesn't really matter. Boy, girl, man, child. You know, you should all be wanting to make things and experiment. It's our nature, and technology is part of what we are. Know thy world, only then can you be at one with it. Well, we're really starting to know our world now, aren't we? And it's fun. Yeah, so it's there, Heaven. That's the one I made myself, looking, following a schematic on Big Clive's channel. So it shows you it's quite an easy hobby to get into. Treat it as a hobby, but also life skills. Some of these, some of the stuff we're going to be presenting and looking at, you can use in real life to, make life easier and get your bills down and heat your own water and things like that. This is what we need to be doing.